Heat transfer. As an introduction, let us just first define the kinds of materials involved in heat transfer, or not. Conductors, materials that allow heat to flow easily. Examples of these would be metals. And insulators. These are materials that slow or block the flow of heat. Things like wood, plastic, fiberglass. Having defined thermal insulators and conductors, we're now in a position to examine the mechanism of heat transfer and the rates of heat transfer. There are three mechanisms of heat transfer: conduction, convection, and radiation. As we go through this, we're going to look at mathematical approaches to both conduction and radiation. Convection is much more complex. Let's look at conduction first. If you remember the definitions of temperature earlier on, we mentioned that temperature is directly related to the average kinetic energy of the molecules in a substance. In a warmer region of a substance, which we have here in the red block on the left, with the temperature T2, the molecules have a higher average kinetic energy than in the cooler region, T1, here on the right. The conduction is the flow of heat due to the transfer of kinetic energy in molecular collisions within the object. Now the rate of heat transfer, delta Q over delta T, depends directly on the relative temperature at both ends, that is T2 minus T1. If there's no difference between the temperatures, the two substances are in thermal equilibrium, and there's not going to be any heat transfer. It's also going to depend directly on the cross-sectional area available for collisions to occur. The bigger the area, the more collisions can occur and the more heat that can be transferred. At the same time, the conductivity has to be inversely proportional to the length along which the heat must pass. The heat has a longer distance to go between the two objects, and as a consequence, it will take longer. The heat transfer will be slower between the two. And then finally, it's going to depend on the material, on something we call the thermal conductivity, or conductivity, K. And this represents the ease of heat transfer. So summing it all up, we have this expression that delta Q over delta T, the heat transfer, is equal to the thermal conductivity, K, times the cross-sectional area of the contact divided by the distance between the two objects, L, multiplied by the temperature difference between the two objects. So again, delta Q over delta T equals Ka divided by L multiplied by T2 minus T1.